Bismillahirrahmanirrahim. Assalamu alaikum warahmatullahi wabarakatuh. Hello friends, welcome back to my YouTube channel. In this video, we will be initiating the part 2 of physical chemistry in G.C.E advanced level chemistry syllabus. So, physical chemistry. Normally, I classify physical chemistry into two major parts, part 1 and part 2. So in part 1 we study the 4th and 5th units. They are gaseous state of matter, gaseous state of matter, which is our 4th unit, and our 5th unit will be energetics. We have already completed these two units, and now we will be focusing on the part 2 of physical chemistry, where we have 3 units. So here we will study unit 11, unit 12 and unit 13, and we have one more remaining unit, that is unit 14, that will be industrial and environmental chemistry, right? So we will study that finally. Now we will study 11, 12 and 13th unit. So the name of 11th unit will be chemical kinetics, and then unit 12 will be chemical equilibrium, and finally unit 13 will be electrochemistry. So in gaseous state of matter, we studied about the organization of particles in 3 principal states of matter and their properties, and then we moved to gas laws, where we studied about Avogadro law, Boyle's law and Charles law. Then we studied the ideal gas equation and performed some calculations based on ideal gas equation, and then we studied about Dalton's law of particle pressure and molecular kinetic theory of gases, and finally we amended the ideal gas equation to be used for real gases as well. Then we moved to energetics. In energetics, we studied system, surrounding and boundary. These are the basic terms in thermochemistry we are using. Then we studied about the properties of a system. We studied about microscopic properties, macroscopic properties, and then we studied about the state of system: spontaneous process, non-spontaneous process, reversible process and irreversible process. Then we moved to enthalpy. Then we studied some types of enthalpy changes, and ultimately we determined the spontaneity of a reaction using Gibbs free energy. Right, now here we are going to study the 11th unit. Before that, let me classify chemical equations based on the rate. Okay, so normally in chemistry we deal with chemical reactions, so we can categorize chemical reactions into irreversible chemical reactions and reversible chemical reaction, whether the reaction occurs only in forward direction or in both backward and forward direction. Okay, so the next category will be reversible chemical reaction. Let me now talk a little bit about irreversible chemical reaction. This is the type of chemical reaction that we have studied so far. For example, if I take NaOH plus HCl, this happens only in the forward direction under normal condition and produce NaCl and water. Right? So basically here we have reactants, and we form products from the reactants, and one more thing you should notice is we use a single direction arrow mark to indicate irreversible chemical reaction, which means this occurs only in the forward direction. From the products we cannot form the reactants back. So this is the important point that we should know about irreversible chemical reaction. Now we will talk a little bit about reversible chemical reaction as well. So reversible chemical reaction means you might have seen some chemical equations with arrow marks like this. This means these type of chemical reactions can occur in both forward and backward directions. So let me write it down here using a different color. So these types of chemical reactions can proceed in both forward and backward directions, right? So the next point you should know is these type of chemical reactions will attain a steady state, which is called a dynamic equilibrium, right? So here a steady state called dynamic equilibrium will be attained. So we will be talking about dynamic equilibrium and the process for dynamic equilibrium in detail in our 12th unit. So now what I wanted to tell you is in chemical kinetics we will be dealing with irreversible chemical reactions, and in the 12th unit only we will be dealing with reversible chemical reaction. Anyhow, let me tell you some example equations for reversible chemical reactions in order to make you familiar with it as well. So one example is examples for irreversible chemical reaction. So one instance that we have come across during our journey is dissociation of weak acids and weak bases. Dissociation of weak acids and weak bases. So this is one of the example where reversible chemical reactions occur, right? So for example, if you have CH3COOH, now you might have seen using double way arrow mark in this type of dissociation of weak acids and bases. So we will get CH3COO minus aqueous and H plus aqueous, which means here partial dissociation occurs. So both forward and backward reactions are happening. Another example is synthesis of ammonia. In industrial chemistry, we will be talking about synthesis of ammonia in detail, but I just want to introduce the chemical reaction happening here. So we will have N2 gas and H2 gas as raw materials in order to produce ammonia gas. So this is also another example for irreversible chemical reactions. Another famous example for irreversible chemical reaction is formation of carbonic acid. Formation of carbonic acid. So formation of carbonic acid. Carbonic acid is formed by making carbon dioxide and H2O liquid react together. So in fizzy drinks you might have stored gases under high pressures. Carbon dioxide gas is stored under or dissolved under high pressure, right? So carbon dioxide, CO2 gas plus H2O liquid becomes H2CO3. This is carbonic acid. So in soft drinks we have dissolved carbon dioxide in water under high pressure, right? So this is another example for irreversible chemical reaction. The main thing that you should know is these irreversible reactions can be shifted back and formed. Now these chemical reactions can be shifted back to form reactants again. Okay. And we will be talking about these irreversible chemical reactions in the next unit. Now what I wanted to teach you is the type of chemical reactions depending on the rate, right? Okay. So now we have to know a term called rate of a chemical reaction, and this is what we are going to learn in chemical kinetics, which is our 11th unit, right? So we will now put a heading chemical kinetics. So in chemical kinetics we will be talking about irreversible chemical reactions only. And in this chapter we will be talking about rates of chemical reactions and the factors affecting the rates of chemical reaction, and how the concentration of reactants and products change over time. So we will be basically sketching diagram for time versus concentration and analyze them, and we will be looking at the mechanisms by which the chemical reactions occur, right? So these are the things that we are going to study in this chemical kinetics. Now let me introduce a term called rate of reaction. Rate of reaction. So rate of reaction is the change happening in unit time, right? So if I want to write a definition for rate of reaction, I can simply write definition the amount of change happening in a chemical reaction is called rate of reaction. So if I transform this sentence into a mathematical expression or equation, I can write chemical reaction or rate of reaction. Rate of reaction is equal to change over time. So now the change that we consider here is the change in concentration. So here the change in concentration. Okay, right. Now if I take a hypothetical equation, A becomes B, now I am going to plot a graph for concentration over time. Concentration over time. Right. So initially the concentration of A is Ca, right? Let's say this is the initial concentration of A. At time is equal to 0, we had no B. So the concentration of B at time t will be equal to 0. With time, what will happen? Now A is converted to B. So the concentration of A will gradually reduce and ultimately it will reach to 0. But with time, what will happen to the concentration of B? It will gradually increase over time. right? So this is concentration of A. Ca means this is concentration of A, and this is the graph for Cb, concentration of B. So I can tell that the unit of rate of reaction will be equal to, so unit of rate of reaction. Sometimes they might ask what is the unit of rate of reaction. So here you see rate of reaction is equal to change divided by time. So the change is considered as the change in concentration. So normally we measure concentration in mole decimeter minus 3, and time is measured in seconds, right? So basically the chemical reactions happen within seconds. So the unit will be equal to mole decimeter minus 3 second minus 1. Now if you measure the time in minutes, then it can be expressed in mole decimeter minus 3 minutes minus 1 as well, right? Okay, now if you consider this graph, I have sketched the trend of concentration of A and B in the same diagram. But now I am going to consider the concentration of only the reactants, right? So here you see this is my graph, this is time, and this is concentration. Now this is the initial concentration of A, and with time it is decreasing, and ultimately it will be totally consumed. Then the concentration of time after the completion of this reaction will be 0. So this is Ca. Now you see gradient of this graph. Gradient of this graph is equal to change in concentration. We can express like this: delta concentration gradient of this graph will be equal to delta concentration divided by delta time, right? So here if you look at the line, this is a curved line, this is not straight line, which means the gradient is not constant, right? So here this is a different gradient, here different gradient, since the slope with the x-axis is varying, okay, right? So now we have two types of rate of reactions. One is initial rate and the other one is average rate, right? So we have two types of rate of reaction: initial rate of reaction, and the other one is average rate of reaction. Okay. So the initial rate of reaction is the rate of reaction when at the initial point of the reaction, when the reaction starts to happen, right? So in that case the initial rate of reactions will be measured. Okay, so this is the, okay, so if I want to write a definition for initial rate of reaction, I can tell this is the rate of reactions that is measured at the beginning of the reaction. Okay, this is the rate of reaction calculated at the beginning of the reaction, right? So now here you see this is the initial concentration of A, and when during the starting period of this reaction we are going to take the difference in time, right? So let's say this is our T1 and we have to find out the corresponding concentration, right? So let's say this is Ct and this is C0. So now we can tell R1 is equal to change. So change is always measured from the change is always calculated by subtracting the initial state from the final state, right? So final concentration, or the instant concentration we can say, minus initial concentration. So now we will just divide it by time also, right? Here we are taking delta T, that is T1, okay, right? So the final concentration or the concentration at time T will be Ct minus C naught divided by T1. So now we know that from the graph we can tell that C naught is greater than Ct. So this value will be negative. So what it indicates is the rate of reactants will decrease with time and the rate of products will increase with time. Okay, right. So what I told is the rate of okay, so rate of reactants decreases and rate of product increases. Why it is happening? Because the concentration, right? So if we are measuring the change within a certain time interval, now we are going to consider the change in concentration. So what happens to the concentration of A, that is the reactant? It decreases. So when it decreases, the gradient also will decrease. So we can tell the rate of reaction will decrease. Here the gradient will be nothing but the rate of reaction. Okay, right. So we talked about initial rate and average rate of reaction. Now consider this scenario. Now this is not a straight line, which means at a certain time interval the gradient is changing, which means we have different rate of reaction. Now let me take it as R1, that is the initial rate of reaction, and with this time interval, right? So let's say this is delta T2, and let's say delta T3. Now I'm going to consider the, let me erase it and draw beautifully so that you can easily understand. Okay, so now if I draw a diagram, if I draw a graph for concentration over time of reactant, okay, right. So within this time interval, let's say, let me call this as delta T1, and let's say the concentration change, this is delta C1, and here this will be equal to, let me use a different color. Okay, so I'm going to measure this concentration within this time interval delta T2, and this is the change of concentration, so this will be delta C2, and again I'm going to measure this, the concentration change within this time interval delta T3, and the concentration change, this will be delta C3. Now if I measure the gradient, so del R1, right? So R1 is equal to nothing but delta C1 divided by delta T1. Now R2 is equal to delta C2 divided by delta T2, and again this is R3 is equal to delta C3 divided by delta T3. Now the average rate of reaction will be equal to, I will call it as R, or R is equal to R1 plus R2 plus R3 by 2. Since, I'm sorry, by 3, right? So how many rates of reactions we are considering? So since I am considering 3 rates of reactions, I have to divide the summation of these rates and divide by 3. Okay, right? So if I am taking n, right? So if I am taking n number of rates of reaction, then I can write a general equation. R will be equal to, this is nothing but the average rate of reaction, R1 plus R2 all the way to Rn divided by n. Okay, right? Now if you look at the trend of this curved line, I can tell a point, right? So the point is, generally when the chemical reaction happens, okay, now when the chemical reaction starts to occur, at that time the rate of reaction will be high. Okay, so like the early bait catches the worm, the rate of reaction at the initial stage will be high, right? So the rate of initial, okay, otherwise we can say the initial rate of reaction will be high in a chemical reaction. This is just a general consideration, right? Because you can just see the slope of this R1. This is high, this seems to be high than the other slopes, right? So we can say the initial rate of reaction will be high, comparatively high in a chemical reaction. Now in practical scenarios, we have 2 methods for determining the rate of reaction. The first method is by measuring the change over a particular period of time, and then the second method will be for a particular amount of change to happen, we have to measure the time, right? So 2 methods of determining rate of reaction. This is what is our next topic. Our next topic is two methods of determining rate of reaction. Okay, right? So the first method will be by measuring the change over a particular period of time. By measuring the time, or otherwise by measuring the change within a particular time interval. The second method will be, for a particular change to happen, we have to measure the time. Here in the first method, the time is constant, the time interval is constant, and in the second method, the change is constant and we are measuring the time, right? By measuring the time for a particular change to happen. Right? So the word particular indicates that they are constant, right? So they are constant. Right. Anyhow, the first method will be more efficient since it has less error. So the first method will be efficient. So in practical scenario, we will be measuring the change within a time interval. Okay, right? So we can say, since the errors are less in the first method, we will consider it as the efficient method. Okay, so here in a chemical reaction, two things are happening. The first one is disappearance of reactants and the formation of products, right? So disappearance of reactants and formation of products. So here for the reactants, R can be written as negative the change in concentration, let's say the change in concentration divided by T, right? And here for this we will be writing the rate of reaction. The equation for the rate of reaction is equal to concentration of B divided by T. So what we have to notice here is, here we have negative since the rate is decreasing. Here we have positive sign since the rate is increasing. So if I consider a chemical equation where we form B from A, right? So the rate of reaction will be equal to minus delta CA divided by delta T, but that will be equal to delta CB divided by delta T. So CA means concentration of A, and delta represents the change, right? So, and this minus indicates that the rate is decreasing. Again, CB is the concentration of the products and delta indicates the change and delta T. So this is what we are going to use in this chapter. And now we have to study about the relationship between reaction rate and stoichiometry. But before that, we have to classify, as I mentioned in the beginning of the video, we have to classify the chemical reactions based on the rate. Now after completing this portion, we will come to the relationship between stoichiometry and the rate of reaction. Okay, right. Now put the heading right. Classification of chemical reactions based or with respect to their based on their rates. Okay. Now we are going to classify the chemical reactions into three categories as very fast or instantaneous reaction, right? So this is happening within a shorter period of time, within very minute amount of time, right? So we know that R is equal to change divided by time, right? So here if I consider the change, that is our constant, that is what we are going to study, right? So we have two methods for determining rate. The first one is by measuring the time taken to encounter a particular amount of change. So here this is constant, so we can tell that R is inversely proportional to time. So when the time decreases, the rate will be high, right? So very fast or instantaneous reaction means the time is very less and the rate is very high. So using conventional methods, we cannot determine the rate of reaction, because you see, if the time is very little, very minute, we cannot, very small, if the time is very small, using our conventional method, we cannot measure the time, so it will give you errors. So we are not going to determine the rate of reactions for these types of reactions. Then we have very slow reaction, okay. So the very slow reaction means the time is very high and the rate is very less, right? So we have to wait for a long time for the reaction to happen. So basically for this type of reactions also, we do not determine the rate. But the third category will be moderate reactions. Moderate reaction. So for these type of moderate reactions, we have many examples. For these, we are going to take these moderate reactions to determine the rate of reactions experimentally. Okay. Okay. Now we will first talk about very fast or instantaneous reactions. Okay. So now the reactants, once the reactants are brought together, suddenly or instantly the products will be formed. So here, using our conventional techniques, we cannot determine the rates of reaction, but using advanced techniques we can measure. But for our purposes, we are not going to bother about these types of reactions, right? So the time duration taken for these types of reaction is 10 power minus 12 to 10 power minus 18. You don't need to remember these values. These are just to indicate how fast the reaction is happening. Okay. Some typical examples for these types of very fast or instantaneous reaction is formation of precipitation reaction. The first one is precipitation reaction. So examples. Right? So examples, precipitation reaction. For example, if you have AgNO3 and NaCl, now here ions are involved, right? So we have Ag plus and NO3 minus, and here we have Na plus and Cl minus in the system, right? So what will happen? This Na plus will react with NO3 and form NaNO3, and then AgCl also will be formed. So AgCl is a precipitate. So since ions are involving here, these reactions will happen faster. And one more example for very fast or instantaneous reaction is titration reaction. Basically acid-base reaction. HCl plus NaOH. Immediately, once you pour NaOH and NaCl, what will happen? NaCl and water will be formed, right? So it is very difficult to measure the time for these types of reaction, but using ultra fast laser spectroscopy and other advanced techniques, we can measure it, but we are not going to bother about those techniques now. Okay. Now we will move to the second category, which is very slow reaction. Second category, very slow reaction. Right? So some examples for slow reaction, very slow reactions are, first one is rusting. Right? The second one is food digestion. Food digestion. Right? So these are some examples for very slow reaction. Now if I consider rusting, what happens in rusting? So Fe plus O2 plus H2O becomes Fe2O3.3H2O, and this is called rust. So here basically the oxidation number of iron is 0. Now it has become plus 3. So this is an oxidation reaction. This is an oxidation reaction. So when we expose iron in the air where we have oxygen and with the presence of moisture, H2O is atmospheric moisture. Atmospheric moisture. What will happen? Rust will be formed on the surface of the iron. So rusting is a natural phenomenon where so when the rusting occurs, it weakens the iron, causing structural damage to the objects like buildings, vehicles and machinery items. So we have to protect the iron or objects made of iron using some methods. We will study about these methods in the electrochemistry, right? Anyhow, we have to know that it is an oxidation reaction where iron loses electrons and becomes worse, right? So here this is an oxidation reaction, right? So now you see iron has lost 3 electrons and become rust, but it is happening in intermediate levels also, but we are not going to bother about those stuffs. Now we will study about rusting in detail in electrochemistry. Now we will move to our topic, that is the third category of chemical reactions, moderate reactions. The third one is very important. That is what we are going to discuss in detail in this course, in this chapter. Moderate reaction. So why we are so much interested in moderate reactions is, here under laboratory condition we can determine the rates of these types of reactions, right? So the rates of these types of reactions are measurable under normal or laboratory condition, lab conditions. So now we will just look at some examples for moderate reaction. The first one will be the decomposition of hydrogen peroxide. Decomposition of hydrogen peroxide. Decomposition of hydrogen peroxide, right? So the equation for decomposition of hydrogen peroxide is H2O2 decomposed to H2O and O2, gas, here liquid, and this is also liquid or aqueous, H2O2 aqueous. Now we will try to balance this chemical equation. Since we have 2 oxygen here, now this is in the number of oxygen in H2O is odd. Here we have even, so we will multiply this by 2. Now altogether we have 4 oxygens in the product side, so we have to multiply this by 2 in order to make the number of oxygen same or equal. So now we will count the number of hydrogen. Here we have 4 hydrogen and here again we have 4 hydrogen. So the equation is balanced now. The second one is decomposition of nitrogen pentoxide. According to your syllabus, we have to know some examples for moderate reactions. I will just introduce one by one. Decomposition of nitrogen peroxide, pentoxide, right? Decomposition of nitrogen pentoxide. So nitrogen pentoxide means N2O5. So it decomposes as N2O4 plus oxygen gas. Now again we will try to balance this as well. Here you just look at the oxygen, number of oxygen. Here even, here even, here odd. So I have to make this odd number even. So I have to just multiply this by 2. Now the number of oxygen in the reactant side is 10. Here we have 4, here we have 2, right? So what I have to do is, keeping oxygen aside, I am going to count the number of nitrogen. Here we have 4 nitrogen, but here we have only 2 nitrogen. So I have to multiply this by 2 to make the number of nitrogen in the product side 4. So now after multiplying the N2O4 by 2, I will count the number of oxygen. So here already I had 10 oxygens. Now 4 into 2, 8 plus 2, 10. So the number of oxygens is also same in the both product and reactant side. So this is how we have to balance this equation. Now the third example is hydrolysis of an ester. The third example is hydrolysis of an ester. Right? So if I take an example for ester, CH3C C2H5 plus hydrolysis using sodium hydroxide, right? So this will return me CH3C, this will yield CH3COONA plus C2H5OH, C2H5OH. Now, okay, if we are given these reactants, now we have to predict the products, right? So I will explain you how to predict the products, right? So if I draw the structure of this ester, CH3C double bond O, C2H5, right? So what will happen is, and we have NaOH also. This NaOH will decompose or dissociate as Na plus and OH minus. Now here what will happen, this bond will be taken by oxygen and this C2O5 will be released. So we have C2O5 with a lone pair, okay, sorry, C2O5 with a positive sign, right? So with a deficiency of electron, right? So with a deficiency of electron, and it has become CH3C double bond O minus. So here we have minus and here we have Na plus. This Na plus will join with this CH3C double O minus and will yield CH3C double O Na, and again this OH minus will pair with C2O5 to produce C2H5OH. C2H5OH. This is supposed to be H, right? So let me explain it again. Clearly understand, don't memorize the reactions, just understand the mechanism happening behind this reaction. So what we have is, we have an ester CH3C double bond O C2H5, right? And we have NaOH also. This NaOH will dissociate as Na plus and OH minus. Okay, since we have already completed organic chemistry and we have studied a lot of mechanisms, so let me just introduce a mechanism for forming soap from fatty acid. So this is called saponification, right? So this is the reverse process of Fischer esterification, where we break ester into soap, right? Okay, so this is just an application of saponification. You don't need to worry about this fancy term saponification because this is not included in A-level syllabus, but when you go to university and take chemistry as a subject, you will study about these mechanisms. But this is very simple, let me explain it to you. The name of this mechanism is saponification, that's all, okay? Right, so here you see we have OH minus. Now this carbon is having slightly positive charge because this is connected to two electronegative oxygen atoms. So here we will have delta plus, and this OH minus will attack this carbon, okay? Right, so when this OH minus attack this carbon, this bond will go to this atom as electrons, right? Because one bond means we have two pairs of electrons. So now I can write this as, this can be written as CH3 CO. We have negative sign also because the double bond in the the double bond has now become single bond, and here we have OH, it has been attacked, and we have OC2H5. Okay, now we have to remove this group. For that we have to this pair should make a bond here, so this will become now CH3 OH C double bond O, and here we have plus, and this has now become C2H5 O minus. Okay, right. Now listen to this. Oh, I'm sorry. Here we have no plus, right? So let me draw it again. Right. So what happens here is now this group has been removed from the okay. So this group has been removed and it has now become O, a single bond, right? So when this pair makes a bond with carbon, now this will go here. So now we will have OC2H5, and we have a negative charge on the oxygen, and here we have CH3 C double bond OH. Now this can be drawn like this for easiness, C double bond OH, right? So again you see this is a carboxylic acid, so this hydrogen can be removed by if this if this negative charged oxygen attacks this hydrogen, now it will now become CH3 C double bond O minus, and this hydrogen has now combined with this negative charge species, so it will become C2H5OH. Again in the solution we have Na plus. Now this Na plus will come and join with this O minus, right? So if now this lone pair will be given to this Na plus. Now this lone pair will make a bond with this electron deficient Na plus, so it will now become Na plus. So the result of the saponification mechanism is CH3COONA. As you can see here, this is nothing but CH3COONA, and here we have C2H5OH, right? So this is how this reaction happens, right? So don't worry about this mechanism. If you understood, then it's okay. If you don't understand, just quit it. Right. Now we have discussed the third reaction that we want to study under moderate reaction. Then now we will study the fourth one. Right. So the fourth one is inversion of sucrose in aqueous solution. Inversion of sucrose in aqueous solution. Right. So I will just explain, or I will just introduce the equation. I don't want to explain much about this equation because we are not going to be using this equation in our A-level chemistry syllabus. So sucrose is C12H22O11 aqueous plus H2O liquid will give you fructose and glucose. So the fructose is C6H12 O6 C6 H12O6, and fructose will be C6 H12O. So this is glucose and this is fructose, right? Okay, so this is just, don't worry about this equation. If you are a biological science student, you may have encountered this type of equation, but if you are a mathematics science, if you are a physical science student, don't worry about it, right? So now we will move to the fifth example, that is the reaction between nitrogen dioxide and carbon monoxide. So nitrogen dioxide NO2 plus carbon monoxide will give you NO gas plus CO2 gas. NO gas plus CO2 gas. Now whenever we write a chemical equation, we have to balance it. So if we balance this chemical equation, here we have only one nitrogen, one carbon, 3 oxygen. So by default the chemical equation is balanced, so we don't need to work further on it. The sixth one is reaction between nitric acid and thiosulfate. So this is a very important equation, chemical reaction that you should remember, right? So thiosulfate, sodium thiosulfate, Na2H2O3 plus HNO3, nitric acid, will yield sulfur solid plus NaNO3 or SO2 gas plus NaNO3 plus H2O liquid. Again, we will try to balance this chemical equation. Also, we will first count the number of sulfurs, right? So here we have 2 sulfurs, and here we have 1 sulfur, and here we have 1 sulfur. So we will put 1 and 1 here. There will be no change. Here also 1. Now if you consider the number of sodium, here we have 2 sodiums, so we have to multiply NaNO3 by 2. Now the number of nitrogens in the product side has become 2, but here we have nitrogens only in nitric acid. Again, the nitric acids also should be multiplied by 2, so we have 2 HNO3. Now if we consider the number of oxygen or number of hydrogen, both are same. So in the reactant side we have hydrogen only in nitric acid, and we have 2 hydrogens, and in the product sides also we have water only. So in water we have 2H, so we will produce 1 mole of H2O. Now we will move to the seventh equation, that will be the reaction between ferric chloride and potassium iodide. Reaction between ferric chloride and potassium iodide. Right. So if I write the chemical equation for this reaction, so we have ferric chloride FeCl3, and we react ferric chloride with potassium iodide, that is Ki. So the products will be I2 and Fe2 plus, I2 and Fe2 plus. So this is a kind of redox reaction where we have plus 3, here the oxidation number of Fe is plus 3, and here plus 2. So here reduction, right? So this is reduction, and here this is -1, since the oxidation number of potassium is plus 1, iodine should be in the -1 stage, and -1 becomes I2. So here this is oxidation. Now for balancing a redox reaction we have another approach. So now we have to balance, or we have to count the number of electrons being exchanged here in this reaction. So here if we want to produce I2, we should have 2I minus, right? So we should have 2I minus, and these two I minus become I2. These two becomes I2. So each I minus should have lost one electron. So here we lose two electrons, right? So minus two electrons, and here you see we have 3 3 plus 3 becomes plus 2, plus 3 becomes plus 2. So Fe3 plus has lost one electron, but in order to make I2 we need to lose two electrons. So here the only species losing electron is Fe3 plus. So we should have two FeCl3 here. So we can take this is also negative 2e. So we should have 2 FeCl3 here. So here 2 FeCl3, and again here also we have 2 Ki, right? Then only the number of electrons being exchanged in this reaction will be same. So now we will have I2 FeCl3. Here we can say FeCl3. If I write this way, you can easily understand. Okay. FeCl2, right? So Fe2 plus means that is nothing but FeCl2 plus we will have KCl also, right? So KCl also, because K is, there is no change in K, right? So and K should combine with an anion, and in the system we have Cl minus as anion. So KCl also will be yielded. So here we have 2 Fe, and we are supposed to multiply this by 2, and here we have 2 iodine. Here also we have 2 iodine in the product side. In the reactant side also the number of iodines is balanced. Now we will look at the number of K. So since we have 2K in the reactant side, we will put 2 in the product side in KCl. Now we will count the number of chlorine and check if they are same. So 2 into 2 in the reactant sides, 2 into 2 in FeCl2 plus 2 in KCl, altogether we have 6. And here in the reactant side in FeCl3 only we have chlorine, so 2 into 3 will be 6. So the number of chlorine is also same. So we have accomplished the mission. That's all. And the last thing is, the last reaction is the 8th one, is the reaction between calcium carbonate and hydrochloric acid. So calcium carbonate plus hydrochloric acid, HCl, will yield you. Now you see we have carbonate ion in acidic medium, it will produce CO2 gas. Then calcium chloride will be formed. Because we can okay, now we can just split the ions involved in calcium carbonate, that is calcium 2 plus and CO3 2 minus, here H plus and Cl minus, right? So due to this acidic medium, carbon CO3 2 minus will produce carbon dioxide, and here we have calcium and chlorine, we have calcium chloride, and this is a kind of acid base reaction, and H2O also will be produced, right? So while balancing the equation, automatically water will come. Now we will see how we can balance this equation. Let me write the equation again so that I can balance it easily. Calcium, okay, calcium carbonate plus HCl gives you CO2 plus calcium chloride plus H2O. Now we will start our procedure by counting the number of calcium. So we have 1 calcium in the reactant side, in the product side also 1 calcium, no worries. And in the reactant side we have 1 carbon, in the product side also we have 1 carbon, no worries. Now we will try to count the number of chlorine in the reactant side and in the product side. So in the reactant side we have 1 Cl in HCl, but in the product side we have 2 chlorines in the calcium chloride. In calcium chloride we have 2 chlorine, right? 2 chlorine. So we are supposed to multiply HCl by 2. Now we have 2 hydrogen in the reactant side. So here 1 water molecule will be formed. And if you count the number of oxygen, that also will be equal in the reactant side and in the product side. So here we have 3 oxygen, here 2 plus 1, 3. So 3 is equal to 3. So the reaction is balanced. So we have in this video we have just discussed the basic principles of rate of chemical reaction, and we studied the classification of chemical equations based on their rate, and we will discuss some questions related to rate of chemical reactions in the next video. Hope you enjoy this video. If you found this video useful, please leave a comment in the comment section and subscribe to my channel, and don't forget to share this video with your friends so that they also can learn something new from this. Okay, so till I meet you in the next video, bye.